This is lesson 5.1. I'm going to say this is 5.1a. This is what you're doing after the test. It's supposed to be a review. The essential question is the same. It's how do you simplify radical expressions? And this is to go along with worksheet 1. Okay, and there's lots of vocabulary in your notes packet in case you're unfamiliar with some of the words that we're going to be using in this unit, and I will make sure to go over them as they come up. Okay, let's see here. All right, so the first example you have is how do you reduce a radical? And we did do this earlier in the semester, okay, in Unit 2 when we were solving. Okay, and so the first thing we want to do is we want to expand the radicand as a product of perfect squares, okay, as many perfect squares as we can. And so I can think about it as, well, 12 could be rewritten as a product of 4 times 3. And then there is the product property of radicals, which says that if I have a full product inside the radicand, and this inside is called the radicand, then I can rewrite this as a product of 2 radicands. Okay, and that's this step 2 here. Now we can square root each radicand that has a perfect square, and the square root of 4 is 2, and the square root of 3 does not have an integer value, and I cannot break it down, so I leave that one inside. And so this is my final answer. And there are some problems that you can try in your packet. I believe this is in there, so let me flip it over. Uh-oh, hang on one moment. Look this up for y'all. Don't usually take that one. There we go. Okay, so these are in your packet. 1 and 2 are the easiest level problems. The blue are in the middle, and the green ones are what I anticipate is the hardest. Go ahead and pause the video here, and you can try a couple of them, and then I'll put the solutions up so you can try them. And here are the solutions, and I'm showing my work in 3 through 6. I believe these solutions are in your packet. So in 1 and 2, they were perfect squares, so I was just able to evaluate. But in 3, I wrote down square root of 8 is the product of 4 and 8, or 4 and 2, and I could square root the 4, so that's how I got the 2 on the outside. 50 is 25 times 2, which gives me 5 root 2. 24 is 4 times 6, so I could break that down to 2 root 6. 6 cannot be broken down into perfect squares, so I leave it like that. And then number 6 was 25 times 5, and I can square root the 25, and I get 5. Okay. And I can't break down 5 either. Okay. So you can check those. Now there's a lot more vocabulary that is coming up, so I want to talk about it in this next example right here. Okay, so you're going to be finding roots other than a 2. And so when we have a cube like this, or 3 right there, that means we're going to find the cube root. The 3 is referred to as the index. Okay. I'm going to put a little side note here, and this is in your packet of vocabulary. Okay. So if I have a radical and it has a small little number out here, we call that number the index. Okay. And this number is significant because it is saying, well, what times itself this many times is the value that's inside the radical. This we call the radicand. I'm going to put an A here, but this is called the radicand. So if I use that word, radicand is just the value inside of the root. Okay? So what times itself n times is A. Okay? And then I'm going to call this one the radical sign. Okay? Or just a radical. Okay, so here, this means that what times itself 3 times is equal to negative 216. Okay? So if I'm thinking of it that way, it's something to the third power is negative 216. Okay, that's another way of thinking the same thing. So I know negative 2 to the third power is 8, so it's not going to be that. Negative 4 to the third power is negative 64, so that's too small. 5 to the third power is 125. Maybe 6 will work. Let me try my math over here on the side. So I have 6 times 6 is 36, and times 6 would be, 6 times 6 is 36. 6 times 3 is 18, plus 1, 196. So it was not negative 6. But I think it is. I think I must have multiplied wrong here. 6 times 6 is 36. Ooh, I didn't carry the right number. Is 3. 6 times 3 is 18. And 18 plus 3 is 21. Oh, so I got it right. So, but then I needed this negative sign here. And so a negative 6 times a negative 6 is a positive 36. And if I multiply that with a negative 6, I would get a negative 216. So I wrote it this way because a cube root and a cube, or something to the third power, are inverses, and these would eliminate. So my final answer is just negative 6. Now I do have a few in the packet. I think these are in the packet that you can try. And the green ones here are probably harder than what you would see throughout the rest of the unit, but I thought I'd throw them out there just so that you could get an idea of what the how to work with the different index. Okay, so pause here and try a couple. And here are my answers. Look at that, number 5, no real root. Okay, now in your homework it's going to say find each real root. If it asks for real root, then squaring a square root of a negative won't be a real root. That would have the I in it. Okay, so that's why that one is no real root. Number 4 is a real root because you can cube root a negative, because a negative 2 times a negative 2 times a negative 2 is a negative 8. And so negatives are okay in odd radicals. But we can't have negatives inside even radicals, like a square root, produce no real solutions or no real roots. Okay, it would have an I in it. Okay, and those are my answers for 6 and 7. The index on 6 and 7 is, the index for 6 is 5, the index for 7 is 7. And so like for 7, I needed something that multiplied by itself 7 times, or something to the 7th power was 128. I knew that number had to be pretty small because if negative 6 to the 3rd power was 216, and this is something to the 7th power, I knew it had to be significantly smaller than 6. So I started with 2, and I played with it that way. There was another thing that I was thinking about. Here, when there's no index visible, like in numbers 2 and 5, the invisible index is a 2. It's implied to be square root of 2. And that's why when you're looking at my example here, I put the index of 2 there. And the reason we do that, why 2 is invisible for square roots, is they are very, very common. We use square roots in several different levels of mathematics, several different classes. We use this one the most in real life, I believe, because it applies to so many different types of things in real life. Okay, the next thing we're going to do is we're going to simplify radicals where the radicand may not be able to have a perfect root. Okay, so here is one that does not have a perfect root. Okay, and this example is in your packet. So something to the third power is not 104, but I could break it down into something to the third power times something else. And so I broke this one down as 8 and 13. And I like the number 8 because 8 is 2 to the third power. So then I could split that up as a product of 2 cube roots. And I could evaluate the cube root of 8. And that's how I'm getting the 2 cube root of 13. Okay, I'm going to do the next example in your notes. Okay, so I put two problems side by side, square root of 48 and cube root of 48, and I have a process here that we use. The first thing we want to do is determine the index of the radical, and I informed you just a few moments ago that if it's missing, the index is 2. And that means I want to find something to the second power so that I could use that inverse property to remove it. So now that I know the index is 2, I want to expand the radicand as a product of factors where one or more factors is raised to the second power. So I know that 4 times 12 would be 48, and I could square root 4, but I could also break down this 12. Okay, so I'm going to split this up, 4 and 12, but I could break up the 12 as well. 12 is 3 times 4, so I'm going to have square root of 4 times square root of 3. And some of you may have picked a bigger square, like square root of 16, because 16 times 3 is also 48, and that would work as well. And now I know that I can square root this because square root of 4 is 2, square root of 4 is 2, and I can't square root 3 or break it down into a perfect square that's different than 1, so I'm going to leave it like that. Now the 2 and the 2 are on the outside, so I'm now going to multiply those together, and I get 4 root 3. Okay. Now there's some extra stuff in here. This is going to come up. I will talk about this in class because it's kind of complicated. But all you really need to do is find the nth root, or the second root in this one, of each factor that was something squared. Okay. And then we multiply the factors inside. If there's more than one number left inside, we multiply it. And then we multiply the ones on the outside. And then sometimes you end up with something that can be broken down further, and so I would keep going. But this one can't be broken down any further, so this is my final answer. So we use almost the exact same process when we do a cube root. Okay, so I'm going to put my process right here. Here we go. Okay, move that out of the way a little bit. Okay, so this time, when we determine our index of the radical, it's a 3. So that means I want to break it down into products where one or more of the factors is cubed, or something to the third power. Okay, so I know that 8 is something to the third power, and so I use 8 a lot. So 8 times 6 is 48. So I'm going to have the cube root of 8 times 6, and I can cube root the 8. So I'm going to split this up as a product of cube root of 8 times the cube root of 6. I can cube root the 8, and that's 2, but I can't cube root the 6. And if I break it down, it'd be 2 times 3, and I can't cube root either of those numbers either. So I leave the cube root of 6 inside, and I end up with that final answer. So now I have a few for you to try. So you can pause here and try a couple of these, and I'll post the solutions in just a moment. And here are my solutions. I predict that there may be some questions on numbers 5 and 6. Okay, so let me go ahead and get out my notes paper and I can go over those before we move on. Okay, so number 5 was the negative square root of 128. And some of you are going to say, oh, but you said we cannot square root a negative. On this one, the negative is on the outside. So a negative on the outside is okay. So it's not on the inside. So it's going to produce a real value. Now this one is a little bit harder to see. It's not a number I'm super familiar with. But 128, I know that 120, 60 goes into 122 times, and so I'm thinking that 64 goes into this one, and again, I'm not 100% sure, so I would think that if 60 times 2 is 120, then 64 times 2 might be 128. So I might check that with a calculator, I might check it with multiplication, and it is 128. And I like the 64 because the 64 is a nice big square number, and I can square root of 64. Square root of 64 is 8, and then my root 2 cannot be square rooted, and then that negative needs to come right down in front. And that's how I got 8, negative 8 root 2. The cube root in number 6, my index is a 3, and so this time I have the negative inside, and I can cube root a negative. Okay, so that's okay to have it here in the middle. 64 and 2 worked with square roots. It just so happens that 64 is a cube value as well. Let's double check it. I think it's 4 to the 3rd power. We know that 4 times 4 is 16. And so if I multiply 4 with 16, I should get 4 to the 3rd power. 4 times 6 is 24. And then carry the 2. 4 times 1 is 4, plus 2 is 6. So that is a cube number also. And so I'm going to put my cube, I'm going to make it a negative 4, because negative 4 times negative 4 is 16, and then times negative 4 will give me negative 64. So I'm going to say that this is a negative 64 times 2. And then I could cube root the negative 64 and get a negative 4. But I cannot cube root the 2 or break down the 2 into anything cubed. So I'm going to leave that inside the radical. That's out of 3, it's a 2. Okay. Alright, there was something else I wanted to go over with you. Let's see. A lot of this I'm going to go over with you in class, so I'm not going to go over this part yet. But I do want to go over this problem here. This is a little bit further into your packet. This example right here. Okay, so you will have questions like this on your test, and it's determine whether the expression is equivalent or not. And so when you're working this out, yes, you can simplify it the same way, and we're going to be doing a lot with these x terms in class on Thursday and Friday. But I need to look at my steps along the way, because these could be variations of this same problem, and I want to be able to check that out. So I'm going to have my cube root 81x to the 7th. Okay, so the cube root of 81, well, 3 to the 3rd power is 27. Okay, so I could put 27 times 3 is 81, so that's 3 to the 4th power. So I could break that down into 27 times 3. And then x to the 7th, I could break that down into x to the 6th times x. Now, why did I pick x to the 6th and x? I can add the exponents, and that would give me x to the 7th, and that's a property of exponents. But also, I picked the 6th because I can cube root a 6. So let me show you guys something interesting here. One of the reasons I was able to cube root before is because I could turn like 27 is 3 to the third power. Okay, and I can't cube root the 3 because I can't write 3 as something to the third power. But I can write x to the 6th power as something to the third power. X squared to the third power is x to the 6th, and that's the power of a power rule because you multiply the exponents. So I'm kind of undoing that process here. Okay, so now I could cube root the 3 to the third. I cannot cube root the 3. I can cube root the x squared to the third power, and I cannot cube root the x. So cube root of 3 to the third is 3. I'm going to leave these two inside, but I can cube root this one. Cube root of x to the 6th is x squared. And some of you might have done that a different way in a previous math class, and that's okay. There's several ways to do these. And now because these two are left inside, I'm going to put them back together, and I get 3x. So I look over here and I see there is one that is identical to mine. So this one is yes. But that doesn't mean that all the rest are no. Okay? Notice here, in this one, they didn't take out the whole x. They left all of the x's inside and still had x to the 7th. Well, if I had left my x squared inside, it would still be x to the 7th, and if I'd only taken out the 3. So one way I could say, I could think about it that way and save myself some time and mark yes, but I can prove it another way. I could break that down, and I know that this is 3 and x squared, x to the 6th times x, and I could repeat that process that I did over there. X squared times x to the third, and now I can take that out, and I would get x squared on the outside, and so that would give me 3x squared cube root of 3x. Let me put those back inside. So this one, when I simplify, I do get that. So that's another reason to show. I can't get a 9 outside. I'm not sure how anybody could get a 9 outside because I can't take the 3 out. This one's stuck inside, so this one's no. There's no way I could get a 9. What about this one down here? This one might have worked too. Again, I'm going to use the technique I did here to prove it on this one. So if I simplify it further, I have my 3x outside. I can't write down the 3 anymore, but I could have said x to the third times x is x to the 4th. And then I couldn't cube root the 3 or the x, so I could leave those inside. But I could cube root the x to the third, and that would give me x. So I'd end up with 3x times x, and then my 3x would be left inside. And then if I multiply my x times x, I would get 3x squared times root 3x. So this one is a yes, even though they didn't first look like correct answers. When I work them out, I see that, they really are correct answers. Excellent. If you have questions, please make sure you bring those questions to me in class on Thursday and Friday, and I will help you out.